This week, we will use the concept of momentum to analyze some more advanced situations, namely, systems in which there is a continuous flow of mass rather than just the motion of discrete objects. The classic example of this is the thrust due to exhaust from a rocket engine. Once again, we will appeal to a differential analysis technique, breaking the flow down into a large number of small elements, analyzing one of the elements in detail, and then generalizing. This is an important example of a situation where the point mass form of Newton's second law of motion, F equals ma, is inadequate, and one must instead use the more general form of the law, F equals dp dt, or the force is equal to the time derivative of the momentum.
We will practice going between reference frames to look at relative velocities in one dimension. Let's say that an observer is standing on the sidewalk, and that observer sees a car drive past to the right at a speed of v car. The observer also sees a bike that's riding to the left at a slower speed, v bike. Now, I'm interested in what the car looks like from the perspective of the bike. The bike sees itself as stationary and sees the world around it moving to the right. To the bike, the observer on the sidewalk appears to be moving to the right with a speed of v bike. The car was moving to the right relative to the reference frame of the observer standing on the sidewalk. So to the bike, the car looks like it's going even faster to the right, with a total speed of v car plus v bike. Let's say later on the biker throws an apple in the direction of her movement and sees this apple travel to the left with a speed of v apple. Now I want to know what an observer sees in the stationary frame on the sidewalk. The apple appears to be traveling a speed v apple faster than the biker, all to the left, so the observer on the sidewalk will see the apple move to the left with a total speed of v apple plus v bike. Now let's say the person throws the apple forward at a speed v apple. What does the car see? To the car, the apple is going to the left at a speed of v car minus v apple. How about the bike? To the bike, the apple is going at a speed of v apple plus v bike to the right.
We would like to now apply the momentum principle to examples of recoil. So recall that the momentum principle is that the external force causes the momentum of the system to change. Now this is a vector equation, so for example, if the external force in the x direction is 0, then the momentum of the system in the x direction, let's say the final momentum, will be equal to the initial momentum. I would like to now apply the momentum principle to an example of recoil. And in our recoil example, we have a person jumping off a cart. So let's just look at how this example can work if we draw momentum diagrams. So suppose we choose a ground frame. And in that ground frame, we have a cart and a person. The person is standing on the cart. And this is t initial. And here, they are at rest. Now, the person we're going to assume to jump horizontally off the cart, and the cart will recoil in the opposite direction. So after the jump, we can describe this picture. The cart, the person is moving with a velocity v. The cart is moving with vc, and the person has jumped with the velocity vp. Now, suppose I choose a different reference frame. That instead of choosing a ground frame as a reference frame, moving with the velocity vc. You can imagine that maybe I have a car here, and that car, you're inside that car, moving with velocity vc, and you're looking at this picture. Then what would our momentum diagrams look like? Well, if I'm moving in a car this way, and in the ground frame, the initial picture is the person in the cart is at rest, then in my moving frame, it actually looks as if the cart and the person are moving in the opposite direction. So let's write that this way. Here's the initial picture, T initial. And in this frame, the person in the cart are moving with VC minus VC. I put an arrow here to indicate that it's opposite the direction of VC there. But their velocity is minus the velocity of the reference frame. After the jump, so here's the person now, the cart is at rest. Why? Because we're in the reference frame moving with VC. So if you're in a car and you're moving at the same speed that the cart has with the ground frame, then in your frame, this cart looks like it's at rest. What about the person jumping off? Well, let's write it this way. So this is the velocity. I'm going to use a symbol U. Now, U, this is what we mean by that. This is the velocity of the person in the moving frame that's moving with velocity vc. That's the velocity of the person as seen by a cart. Sometimes we call this the velocity of the person relative to the cart. What does that word relative to the cart mean? Well, you can see in this picture, in this moving frame, the cart is at rest and the person jumps with the speed u, velocity u, relative to the cart. So these are our momentum diagrams for a ground frame in which the person in the cart start at rest, the person jumps off. I can put an arrow here, but it's really information is in that vector. The cart is moving. In a frame moving with the velocity of the cart, then what does my picture look like? Well, the cart and the person initially are moving opposite direction. Again, you're moving this way. The cart looks like it's moving that way if you're inside the car. And the final state, person, cart is at rest, and the person is jumping with the velocity u relative to the cart. Now, our question now is how do we relate these two velocities, u and vp? What are u and vp? Vp is the velocity of the person in the ground frame, and u is the velocity of the person in the moving frame. Well, we've already seen our equation for how to get velocities in different frames. We have that vp equals the relative velocity of the two frames plus the velocity in the moving frame. So what we have is this is the velocity of the person. We'll just clean that up. Of the person in the ground frame. V is the relative velocity of the two frames. So here we have that V is the velocity of the cart because you're in a frame moving with VC with respect to the ground. And U is the velocity of the person in the moving frame. So this is how we can show the same type of interaction in two different reference frames. Next, we'll figure out what these velocities are. So we've now drawn pictures of the interaction of a person jumping off a cart in both the ground frame and a reference frame moving with velocity vc, which is the final speed of the cart. These were pictures in the reference frame moving with vc, and these are the pictures, momentum diagrams of the person and the cart in the ground frame. Now we would like to apply the momentum principle to solve for vp and vc. We are given that the velocity of the person in the moving frame, u, we'll treat this as a given quantity. And we'll express the velocity vc, and so we want to find vc and vp in terms of u, mp, and MC. Now, we'll use the ground frame first. And our assumption here is that the person jumped horizontally and that there are no external forces in the horizontal direction. So all of the vectors we've drawn are horizontal, and there's no external forces in the horizontal direction. Then we know that the initial momentum of the system is equal to the final momentum of the system. In our initial picture, nothing is moving. And in our final picture, we have m cart, v cart, plus m person, v person is 0. Now, recall that we also showed that the velocity of the person in the ground frame is related to the velocity of the person in the moving frame by adding the relative velocity of the two frames. The relative velocity of the two frames is the velocity of the car, vc. So what we have is vc plus u. So this is how vp is related to u. And now I can use this starred equation to write it as 0 equals mc vc plus mp times vc plus u. And by adding terms, I get that mc plus mp vc equals minus mpu, or the velocity of the cart is equal to minus mpu divided by mc plus mp. Now that I have the velocity of the cart, I can just substitute that in here to find the velocity of the person, which, remember, was the velocity of the cart plus u. So now I've solved this problem in the ground frame. Next, I'll do the same analysis in the moving frame. So we've been trying to find the velocity of the cart and the velocity of the person in terms of the relative velocity of the person jumping in the reference frame of the moving cart, the mass of the person, and the mass of the cart. We've already solved this in the ground frame. Now I would like to solve this in which my reference frame is the moving frame. So our pictures in the moving frame were actually much easier. Because the moving frame is traveling with the final speed of the cart, at the final interaction, after the interaction is done, in this moving frame, the cart is at rest. They're moving together. You're sitting in the cart. You're moving at the same speed. The person jumped off with speed u relative to the cart. The tricky part was to realize that in the ground frame, when the cart is at rest here in the ground frame, an observer moving with speed vc would see the person in the cart moving backwards in the moving frame with the speed minus vc. So now we can apply the momentum principle to these two states. In the moving frame, we have that momentum of the system initially equals momentum of the system finally. Now the initial momentum is just minus mp plus m cart v cart. Notice the minus v cart. And the final momentum is equal to just m person u. And so we see that v cart equals minus m person u over m person plus mc, which is exactly the same result that we got in the ground frame, but it was actually much easier to solve in the moving frame.